Hello, Hendrik. How are you?
Hello, Chris. Nice evening to you. It's evening here in the Netherlands, and I think morning for you in Canada, but that's all fine. In Holland, we have, where I'm located, we currently have a bit of a cloudy sky, although it's patchy, but I wouldn't gamble on doing some kind of live session with an actual telescope out in the field. I'm really hoping we can still have that opportunity at some point, but yeah, the skies here are challenging to say the least at the moment. But fear not, I've had the opportunity to go to sunny Switzerland, and especially for this webinar, take a bit of a recording of an actual polar alignment session from a balcony. But before I dive into that, allow me to briefly go over what is polar alignment for those of you who are just getting into this hobby and have heard the term bashed around so many times and want to know what is this thing all about. So let me introduce to you, I hope everybody can see it well, but let's hope so, to this little telescope here. Well, it's not a telescope, this is actually a mount. And one of the features of this particular mount is that it is an equatorial mount. And you have basically two flavors. The first flavor is altitude azimuth or Dobsonian, typically, and it moves horizontally like this, up and down. Unfortunately, I don't have one with me, but I think you get the idea. And the other one, the equatorial mount class or German equatorial mount class, you can see here. Now, this mount, and this is a little known fact, actually has not two, but four axes. Let me demonstrate each one in turn. The first axis is only used for setting it up. And this is the azimuth. So you can turn it horizontally like this, and this is the azimuthal axis. The other axis, which is also only used for initial setup, is the altitude axis. This is simply going up and down, like so. Then finally, and this will be shown a bit better in the video that I will show with you in a second, are the right ascension axis, this one, and the declination axis. Here on top is typically where you mount the telescope. Now, the nice feature about an equatorial mount, and this is how they were designed, is that it only takes one axis to track the stars. And this was, especially in the beginning, immensely useful because it really simplified a lot of the control electronics. You could just essentially put a very closely moving, accurately moving motor just on the right ascension axis, and it would magically move around the stars and or follow the stars, no matter on Earth where you are. The only little detail here is that your mount's axis, so this is this one, which I'm pointing right here, right through the heart of your mount. If you would bore a hole through it, and in fact, almost all mount manufacturers have done so, you can remove the end caps. Well, this one is empty, but you can actually look right through it. And the trick to get it tracking really nicely is that this axis must be aligned with your local, well, forgive me for lacking the proper English word, but with your local polar axis, which typically in the Northern Hemisphere points towards Polaris. Now, the neat thing here in Holland is that Polaris is quite high in the sky, so it's easily visible. In fact, the altitude of Polaris, wherever you are on Earth, is essentially your latitude. So here it's 52 degrees above the northern horizon. If you are at the North Pole, which is 90 degrees latitude, it's straight up at zenith. So this is the only spot on Earth, together with the South Pole, where your horizontal mount system coincides exactly with an equatorial mount system. On the equator, on the other hand, the latitude is 0, so it's really on the horizon, which is a bit of a special case, and that also counts as being equal to altitude azimuth mount, but having the axis reversed. So the trick to do is you have to locate Polaris, if you look through this, before you can start imaging. And if you have done so, then you can easily track the stars by just moving the single axis. So the process of aligning your mount like this for your imaging session, this is called polar alignment. Now, there's been a lot of things being said about polar alignment over the years, how accurate it must be, how to do it. Many methods have been proposed over the years, but suffice it to say that I found it quite interesting to see if I can come up with a new way to do polar alignment for those of you, and this is really a big problem, if you cannot see Polaris, for example. How do you do that? Suppose you're imaging from a balcony that only has a view of the south, or you're imaging in your garden, but the entire northern part of the sky is blocked by some trees, so you cannot see Polaris. Even worse, for those of you on the southern hemisphere, though blessed with very interesting skies, don't have a Polaris at all, because there's actually just a kind of small group of stars, very faint, that you'd have to center. None of them is particularly close at the center. So the method I'm going to share with you using StarAid basically does not require you to have any particular view of Polaris or either the southern hemisphere if you're on the southern side of the Earth. Let me see if I can share my screen to show you the actual session. Here we go. Chris, is this visible clearly?
Yes, it's fine. It's fine.
Thank you. So here I have my setup, and you can see it's the same mount. It's a well-known brand, and it's a very common mount. It's not that expensive and tracking quite nicely for most purposes. You can see that I have set it up with StarAid on top with the yellow cable sticking out. And you can see along this counterweight bar also the major axis, the right ascension axis that turns. And here is basically what we need to polar align. Now, as you can see, basically from the outline of the balcony, this one is south facing, strictly speaking, a bit to the southeast, and I did not have a view of Polaris. So where to start? Well, first of all, if you look at my original presentation, like moving the mount like so, I can do a pretty large movement on the altitude axis and the azimuth axis because I removed the screws. But in actual practice, this movement is restricted. So some really initial kind of setup is definitely quite essential. And in order to do that, and I did not show this process, you can take a compass where you are, and you can roughly align your mount facing north or facing south, depending on the place on Earth where you are. So north for northern hemisphere and south for southern hemisphere. The next thing to do is adjust your altitude axis, this one, to match, roughly speaking, with your latitude. And if you do this properly, and you can do this with a little bit of practice in no time at all, you can be within a few degrees of the pole already. Then the only thing that's required to do a final tuning is just to follow this procedure. So please have a look. Here I'm demonstrating it for clarity again. Here I'm fiddling a bit with the knobs, as everybody's been experiencing. So the axis I'm turning right now is the right ascension axis. This is the axis that needs to turn to track the stars. The axis that I'm now going to turn is the declination axis. Using both axes, you can position any spot in the sky that you want to catch. Okay, now I'm locking the axis and I'm beginning the polar alignment session. I've already configured the proper location in my StarAid. So I've made a connection with the Wi-Fi. I've set my location in Switzerland where I'm located at. Your location should be pretty close, but it doesn't need to be, it can be a near city or a near village. So any place within, say, 10 miles or 20 kilometers is sufficiently okay. Closer the better, of course, but it should not be more than, say, 20 kilometers away. Alternatively, you can enter your precise geo coordinates as well. Now, I've basically now put, I fixed the mount at any place that I have a clear view of the stars, and I'm pressing recognize, so the next step. And now it has solved my first position. So as you can see here, it has matched the location in the sky I'm pointing at. The next trick to do this polar alignment is just to move the mount on the right ascension axis a little bit further. Here we go. So here I move it a little bit to the next point and I press the button again. While it is still recognizing, as you can see here, I'm free to move the mount already away. Sometimes recognition can take within a second, and sometimes it will take a few seconds. But that's okay, it will almost always find the location. So the previous position has now been solved, and basically the new coordinates are given here. Doesn't really matter that much which they are particularly. And the app will basically say, keep going, get the next points. So now I'm going to get the next point. And here we already see, once we have 3 points, a first indication of a solution. It's not pretty good. So as you can see on the top here, according to the algorithm, it says, hey, your alignment error, so the offset between the desired axis and what you're actually pointing at, is 31 degrees, which is way too large. However, the accuracy is 32 degrees also. So essentially it's telling me, hey, I don't really know exactly yet with sufficient accuracy where I'm pointing at. So gather more data and the accuracy will improve. Let's try that. Next point. You can already see from 32 degrees, it went down to 11 degrees, although the accuracy is still quite poor. Let's move a bit further up the circle and let's see where you get at now. Aha, this is much better. So here we see that we are at 43 arc minutes, essentially 44 arc minutes, slightly less than 1 degree. And we have an accuracy of about 2 arc minutes. This is green, so basically the indicated action now is finish. So we have determined the polar alignment error with sufficient accuracy. The next step is we need to make the adjustments in the azimuth or altitude axis. You're free to pick any axis you like. In this one, I start with the azimuth. And then I go to the help screen. And in the bottom screen here, you can basically see some specifics. So right here in the crosshair center, there is where we need to end up. The blue dot is where we're currently pointing at with this axis, the one of the core of the mount. The total error between this angle and the actual point where we need to point it is 1 degree, which breaks down into about 26 arc minutes altitude, up and down, and azimuth about 1 degree to the right. And the trick now is to start one axis and to move it more slowly towards the middle. Now, it is a live update, so while I'm looking at the screen, I'm turning here in the bottom, I'm turning the mount axis, and you can see that the dot is moving in that direction. Now, you can, if you want to fix the mount, so you have to, don't forget to put the screws tight back together again. It will tend to move a bit further, but that's okay. I will explain later why. The next axis was the altitude axis, which I'm going to do then. So that's the other buttons. And as we do that, we can move it up and down. In this case, we need to go up. And once we are sufficiently close and we're happy with the result, we basically lock the axis tight and we finish up. And that's it. We're done. We have finished the polar alignment. Now, to clarify the things, I've paused it a bit, but the entire procedure here takes literally only a few minutes. And essentially, I don't need to have a clear view of Polaris at all. And if you remember from the start of the video, I just put up my scope at any point in the sky without paying too much attention where. It really doesn't matter. Now, one thing that you can do after you've done your polar alignment is you can check the polar alignment again. So we moved the telescope, in this case, StarAid, to a slightly different position, just as a cross-check. You don't need to be doing this, but if you're curious, then we basically perform the same procedure again, and you can make another tuning if you like. One thing to keep in mind before you start this, and this is just a practical limitation, it's not a fundamental one, is that your mount needs to be level in order to make these corrections. So typically most mounts, they have a kind of indicator to see if you're really level or not, and that would be wise to use to make sure it's more or less level. So here we make the check again, and after we've made the check, we're ready to start guiding. Now, that kind of brings me to the next topic, guiding and polar alignment. So how accurate should your polar alignment result really be? Some people have tried StarAid out in the field and they've reported that if they repeat the procedure a couple of times, it tends to give slightly different locations. Not by much, but it can vary a bit. Some people say you should really go to the fullest extent and do polar alignment down to the final arc second. Well, I can assure you that is totally waste of effort. It's nice if you want to try it out, but it doesn't really bring you better images. First of all, those that claim you can get 10 arc second accuracy with polar alignment, I tend to doubt that. First of all, because due to the mechanics of the mount and 10 arc seconds being really tiny amount of angle, you can easily get that kind of distortion if you move your mount to the next place and to the other place. Due to the weight and shifting load balance, nothing is infinitely stiff, so it can sag a bit and you can get already more error than that. The other question really, and this is more to the point, what does it bring? Does it bring you better images? No. The only thing that you need to do the polar alignment for is for your autoguider to be able to catch up with the corrections. So whenever you are within 1 degree of the pole, most of the time your mount will be able to keep up with guiding. Now, what other effect do you need? Can you expect if you're really not that well polar aligned? Say, okay, I'm going to misalign deliberately 20 degrees. Well, even if your mount can keep up, if you have a very high guiding rate, for example, what you will see, and this is well known to people that are using altitude azimuth mounts, Dobsonian mounts, is you can see some kind of field rotation. And this is not that hard to visualize, because suppose you're starting in the east, and if your mount keeps tracking, it just tries to keep straight like this to follow the star. However, you can see if you try to follow that arc that the star does, it actually moves like this, and then into meridian and then goes down again. So this angle difference translates to your images appearing to be rotated. But these days, that's really not a big of a problem. If you take short subs, any kind of residual angle will just rotate out during the alignment process of your final image processing. And even if you're mostly reasonably well polar aligned, it will not show up that much, even if you do 15-minute subs. Now that we've addressed polar alignment, the other question is guiding. What do you need to do proper guiding? Well, there are a couple of options there. So this is the one that I showed last time. This is the StarAid with the 100mm focal length guiding optics. Some people think that you really need a much longer focal length to do effective guiding. Some numbers have been set, so you need to have a focal length of about 1/10 of the focal length of your main imager. So if you use a C14 Cassegrain with 4-meter focal length, you'd need to have a guide scope of at least 400mm. Well, that's totally not true. Maybe it was true and had an element of truth to it in days long past, when people really had to look through the eyepiece and manually guide their scope by making manual adjustments. But these days, due to image processing algorithms and fast computers, we don't need to do that at all. There are a couple of different guide scopes that I want to show you. For example, this is a really nice one. This is a 200mm focal length one. It's quite hefty, but very good. This one is actually a Borg mini guide. It's f7, 174mm, nice and compact. Well, this one you've already seen, 100mm, f2.8. This is also a well-known one, 120mm, f4. And finally, and this is kind of interesting one, just a general CCTV lens, 50mm, very small, very compact. Which one of these would be better at guiding, especially if you're using a long focal length? Well, people would typically say, well, pick the biggest one, 200mm, that will give you the most accurate results. But is that really the case? So I did a small experiment to find that out. Let me show you the result. First, see if I can kick off the screen share. Here we go. So here's the nice result. It's a graph, and I will explain you a bit what was measured here. I put StarAid on a 14mm focal length CCTV lens, way smaller than anything people would care to use for guiding in the actual field. And what I did next is, once it gathered a log, I stopped the guiding corrections and I registered the result and plotted them afterwards. And what you would expect if you turn off guiding and turn off your mount's tracking, you would see that the stars slowly drift out of the field. Now, StarAid, as I explained in the previous session, does multi-star guiding. So you see many stars in the entire field of view, and it keeps accurate trackers on each of them, and will basically put an analysis of what all those stars together are saying about the center of my frame right now. So some stars here can go this way, and in the other frame, they can go like that way, but these movements tend to average each other out. And the center basically shows you the black line. So here we start, time in seconds, 50 seconds, value 0. So here we have no error at all. And as we turn off tracking, you can see that there's a big error accumulating here, as we would expect, because we're not tracking anymore. If we look closer, we can see this. So we zoom in on a small piece, and here you can see each individual data point. What it also nicely shows is, in this case, that StarAid was locking onto the stars 5 times per second and giving the center values of your frame 5 times per second. This is the expected line, the red one, the average one. But now I'm going to look at the differences, because you can see some points are above it and some points are below it. What does that say to us? If I do that, you get basically a spread. And this spread, error spread, is basically an indication of how accurate my 40mm lens was able to distinguish the movements. What is the natural error? Now, it turns out, if you analyze this data, that the expected error, or the error that came out of the data, is half an arc second. Ladies and gentlemen, half an arc second with a 40mm focal length guide lens. Now, if we up that to our 100mm one, this one, nice and compact, you can see that that is 2.5 times larger focal length. So quite reasonably, you would see that it theoretically would be able to guide down to, well, let's say about 200 milliarc seconds, which also bears out 0.2 arc seconds, which also bears out in practice. Now, there are very few places on Earth where the seeing is less than 0.2 arc seconds. Does it really make sense to use this one? Well, no, because one big disadvantage of using such a large guide scope is, first of all, it's very heavy. If you're on the move and you need something light and portable, this is really adding a lot of unnecessary weight to it. The other thing, the weight itself can go as flexure. So cables are sticking out, so it can sag and shift as your imaging session proceeds during the night. But more importantly, the polar alignment we saw before, the final adjustment phase, what really helps there is if you see a lot of stars. So you need a large field of view to make that effectively work. And if you use a long focal length guide scope, your field of view reduces. The amount of stars you're able to see is smaller. So there must be some kind of sweet spot. Well, 50mm is really pushing it, 40mm even more. I would basically say, from all the data that I've gathered, that 100 to 130mm is really an excellent focal length. That's it. That's basically concludes most of my presentation for tonight.